Thank you all for coming. Welcome to lecture 5 of our course. I hope you're enjoying the course so far. Last lecture I wanted to do, but I couldn't because I had a flu and I couldn't really speak. This week it's much better. I think Tanush did a very good job doing the last lecture. This lecture today will be on computer vision. The lecture itself will be a bit more dry because we have a bit less quizzes, a bit less programming or live programming, but we need to go through some of the basic elements, and then afterwards we have the tutorial where you are able to put all these elements together and actually program yourself. And that's what we do now. So in green we have the convolutions plus a ReLU. So I told you that one we usually have together. So the nonlinearity and the convolution. Convolution was just another name for filter or kernel. Then we have the pooling. Here people decided to use max pooling. Maybe mean or average pooling works as well. I invite you to try it out as well. There's always a bit of, arbitrary decision making. I'm sure other people used other configurations here. If you add another 5 layers, would it be better or worse? I don't know. You can try it out. And then we have usually a fixed input size for these models. And I can come back to that later on, but let's first take it as given. So we have a fixed input size, and then we add the first layer. Again, green was convolution plus ReLU. And this first layer here has 64 filters, has a kernel size 3 by 3, and padding equal to 1. And some people ask me in between, like what do you do? How do you decide what padding? How do you decide what kernel size? Well, in most cases, you don't decide, because what you do is you look at Google, Facebook, you check out what is their newest model, and you just take their architecture. Because in the end we're chemical engineers and we apply those models. And usually if you download a model from Facebook, Google, whoever, usually these are pre-trained. So out of the box, they're not too bad. And you can easily apply them to your own applications. And that's a big advantage, because if you build these models from scratch, if you train these models from scratch, you need a big computer. And you need a bit of time, and you need to tune all of these parameters a bit, and that's a real pain. And it will likely not be better than just taking a model from Facebook and using that. But still, we should understand what's inside, and we should understand how it's built up. And once you understand it, you can also look at 3 different architectures and get a bit of a feeling of, well, hey, this one is a bit more complex. This one can also handle larger images, and so on. So we start with this convolutional layer with the nonlinearity. Again, 64 filters, 3 by 3, padding 1. So what we want to practice a bit is apply this amazing formula to think about what is the output of this, right? And again, formula IP minus F plus 2P divided by S. IP was the input dimensionality. Well, we had that. That's 224 by 224. So that's what we have here. F was a filter size. It's 3 by 3. P is padding, 2 times 1. And then S is what is it? Stride. Thank you. Sorry. The stride. And that is also defined as 1. So the output is again the same image size actually. So output is 224, 224, and then we have here the 64 filters, and therefore the 64 channels that we have now. Then we add the same kind of layer again. Surprisingly, the result is the same. And then we add a max pooling. So we try to, at some point, reduce dimensionality a bit. Max pooling, you also know. Here we have a stride, we have the pooling size. You can again calculate the output dimensionality. And then we repeat that procedure. We add convolutional layers, we add a pooling layer, We add convolutional layers, we add a pooling layer, and so on. If you want, you can calculate all of them. And then at some point, you end up with a small image. I'm not sure if we have, no, we don't have the size here separated. And then afterwards, we add this red thing here, and that was a standard neural network. The feed-forward neural network. Some people refer to it as MLP, multi-layer perceptron. It's basically what you learned in the first lecture, in the second lecture from Case, right? So this one is a modern convolutional neural network architecture. And if you were to implement that manually in Python, that would be a lot of work and would be probably not as efficient as it could be and as it should be. So what people do is, well, they provide that and then it's easy to use. And one library where you have such models available is Torch. So you can import the neural networks from Torch. There's something like Torch Vision, which is for computer vision in Torch. And you can include, you can load models there here. And one standard model is this VGG16. So basically, by just saying models.vgg16, well, you create an instance of this particular model. And if you want to think about how it looks like, well, you can say summary VGG16, and it will tell you all these layers here. And well, that's just an ugly way of giving you this image here. So let's test if it's actually correct. So the first feature map should be 224, 224, 64. 224, 224, 64. I don't know what the -1 stands for. Batch size, amazing. Then you also see how many parameters are inside. And you can calculate that because, you just need to think about the dimension of the matrix because each of these entries is actually parameter value. And if you do that for everything, you recognize that, I don't know, you end up with 2.5 million, 2.5 million, 1 million, here's another million, so 5, 6, 7 million parameters or so. And that's a model that is relatively old and relatively small. So if you look at modern machine learning models for computer vision, they may have a few million more. Okay. So this is essentially where the magic comes in a bit, right? So that looks extremely complex, and that looks somehow strange. I mean, we know that filters extract some kind of features or can in principle do it. But then having the machine learning model figuring out all of that on its own just by giving a few examples, that many people didn't expect to work for a long time, and that also didn't work for a long time until people increased the size of these models and just trained them longer and had better computers available. And now what people do is, to some extent, they actually increase the size of these models and observe that they get better. And they just add more data. And with more data, I mean, for most of these models, you want to have round about 1,000 instances per category or so. So that's where you say, hey, that really works well. Nowadays, people are able to reduce this number of samples significantly through other techniques that we don't cover here. So models are getting better with less data. But in most cases, what you really want to do is, well, you want to have a lot of data, a lot of labeled data, no errors in your labeling. And what you want is you want to get some model from, like some established model that is already trained by someone else. And then instead of retraining it from scratch, what you do is you take their model and you fine-tune it a bit on your data. And I don't have a slide on that, but what I mean with fine-tuning is basically, to some extent, you could say, hey, all of this part here, that is just about getting an image to a vector, right? And if this model is trained on 1,000 categories, on 10 million images, I assume it works fairly well already, so I don't even want to touch it. So one option that you can do is you can say, I have now my small data set, So few images, few categories. So what I do is I take the images in, and all of this part I freeze. I don't want to touch anymore. I just say like the parameters stay as they are, and I only train this part again. And that's what you did in your, first assignment, and that just works. Or you say, well, this one all works, but I think I can still improve the parameters a bit by just giving it my real data, and then you still fine-tune those models. But in most cases, don't start from scratch because that will be too expensive and too difficult. We have, I think, an additional part of the assignment is to actually train this VGG16 model, but I think that will likely not work on your computers. So you would need to go to either a supercomputer or to something like, I think Google Colab can do that already. Or if, I'm sure some of your gamers, so if you have like a graphic card at home in your computer, that works as well, right? But without a graphic card, it's a bit tedious and might take. You're laughing. You have a good computer.
No, my computer would melt.
Okay. Yeah. Sorry to hear that. Yeah, same for me here. But you can also try Google Colab. I think there you have like reasonably good graphic cards or access to graphic cards that work reasonably good, and I think you can run them for like 20 minutes for free. Is that? Yeah, yeah. So that should be enough to train your model on a few epoch as well.